What I'm going to first do is to try to re-express Z1 and Z2 and Z3 into the Euler form. So for Z1, to express it into the Euler form, let's first find the modulus of Z1, and that will be square root of 1 square plus square root of 3 square. So we have a square root of 4, which is going to be 2. We will also find the argument of this. So in an Argand diagram, let's do a quick sketch of it. The argument is going to be here, and the horizontal distance here is 1. The vertical distance here is square root of 3. So from this, I can deduce the argument of Z1 as, which is this angle here. So it is going to be tangent inverse of square root of 3 over 1. And this is equal to pi over 3. Therefore, we know Z1 can be expressed as 2e to the power of I pi over 3. Let's go for Z2 now. We want to express this in the form of re to the power of I theta. So let's find out what is the modulus of Z2. This is going to be square root of 1 square plus 1 square. This is square root of 2. And for its argument, we are going to have something that is like this. The argument is going to be this. Here is going to be 1, and this is going to be minus 1. So it is going to be in the fourth quadrant. The argument of Z2 is going to be minus of the basic angle, which is tangent inverse of 1 over 1. And this is equal to minus of pi over 4. Therefore, we know Z2 is going to be equal to square root of 2e to the power of minus I of pi over 4, Z2. As for Z3, I guess this is pretty simple, because Z3, which is already in the trigonometric form, if I want to rewrite it into the Euler form, the modulus is simply 2. The argument is just pi over 6. So we have Z1 in the Euler form, Z2 in the Euler form, and Z3 is also in the Euler form, which makes it extremely easy now for us to combine them together to form a Z1 divided by Z2 times Z3. We want to rewrite this entire complex number into another Euler form. So Z1 in its Euler form is 2e to the power of I pi over 3. Z2 is square root of 2e to the power of minus I pi over 4, and Z3 is 2e to the power of I of pi over 6. So for the overall modulus, we have a 2 divided by square root of 2 divided by 2, which is 1 over square root of 2, because this 2 and this 2 can be cancelled. As for its overall argument, we just need to apply indices. So that will be pi over 3, I times of pi over 3, but we are going to be factorizing out I. So pi over 3 minus pi over 4 becomes plus pi over 4, then minus pi over 6. And this is equal to 1 over square root of 2 e to the power of I. This is equal to 5 pi over 12. So rewriting this into the trigonometric form, it is 1 over square root of 2. Then we have a cosine of 5 pi over 12 plus I sine of 5 pi over 12. The first thing that I'm going to do is to let Z4 assume an Euler form, a general Euler form, so re to the power of I theta. And as for Z1 times Z4 divided by Z2 times Z3, which is given to us by the question, I'm going to break it up into two parts. The first part, I will go for a Z1 divided by Z2 times Z3. Then multiply by Z4. This is going to be the second part. And the reason why I am doing this is because from the previous part, we have already gotten the Euler form of this expression. That is why we can now express this as 1 over square root of 2 e to the power of I 5 pi over 12. And as for Z4, let's continue to make use of the general Euler form. So we have this now multiply by this, which we can then form an overall Euler form for this, which will be 1 over square root of 2 times r over square root of 2. Then e to the power of I 5 pi over 12 plus theta. I'm going to re-express this into the trigonometric form. So I have this, then it is going to be cosine of 5 pi over 12 plus theta plus I sine of 5 pi over 12 plus theta. The reason why I'm doing this is because it is going to be useful later. I'm going to show you in a while. So according to the question, the modulus of z1 times z4 divided by z2 times z3, according to the question, this is equal to 1. And according to what we have came up with, we know that the modulus is also r over square root of 2. So this is equal to 1. This tells me that r is equal to square root of 2. And what is r? R is actually the modulus of z4. So we already start to find out some stuff about z4. Let's see whether we can find theta. According to what the question says, this is going to be a purely imaginary number, which means that if it is purely imaginary, this real portion, it has to be equal to 0, because it is going to be purely imaginary, so it will only have this part that has I. So we are going to let the real portion of z1, z4 divided by z2, z3, we will let this be equal to 0. And this actually consists of r over square root of 2. So r over square root of 2 cosine of 5 pi over 12 plus theta is equal to 0, but it doesn't really matter because I can just divide this across to the other side, which will leave me with a cosine 5 pi over 12 plus theta is equal to 0. So this 5 pi over 12 plus theta, it will be plus or minus pi over 2, minus pi over 2 or pi over 2. And the reason why I am writing it to be just minus pi over 2 and pi over 2 and rejecting all the rest of the possible values of angles that will cause cosine to be 0 is because for this particular question, it did mention to me that theta over here is going to be between minus pi and pi. So I'm keeping 5 pi over 12 plus theta to be either this or this, so that theta, which is going to be minus pi over 2 minus 5 pi over 12, or pi over 2 minus 5 pi over 12, will assume two possible values. One is going to be this minus 11 pi over 12. The other one is going to be equal to pi over 12. And these two values will be the only two values of theta that such that theta is going to be between minus pi and pi. So this will, and this theta is actually the argument of Z4. So we have the modulus of Z4 and we have the argument of Z4. This can help us to write down the two possible values of Z4 in the trigonometric form, and they will be square root of 2. Then here we have a cosine of minus 11 pi over 12 plus I sine of minus 11 pi over 12. And another possible value for Z4 will be square root of 2. The modulus of Z4 is only square root of 2. And for its argument, I'm going to pick the other one. So that will be cosine of pi over 12 plus I sine of pi over 12.